All right, pre-cal 12. Here's video number 7. Let's get after it. We're going to do composite functions. This is where we input an entire function into our existing function input. So yeah, that sounds fun, but that's what we're going to look at. So what does it mean? We're now looking at, this is not a dot anymore. Remember when we just finished doing arithmetic combinations, we used dot as multiplication, which is why we started writing it more like just f times g of x. Because what we have here, this is not f times, this means f of g, or f composed of g. It means that the input of your first function is now another entire function. So let's see that in action. So if f of x is equal to x squared, so that's one function, and then g of x is another function, 2x minus 1, what is f of g of x? So remember that when you have f, if we had, say, this is totally random, if we had f of x equals x plus 1, and then we said, okay, well, what's f of 3? We substituted x for 3, so we substitute x for 3, and we would get f of 3 equals 4. That was basic function notation. But what we're doing now is we are substituting an entire new function in, and I'm going to show you two ways to do it. One is what we call abstract, and the other is using a specific value, and you'll find that the specific value is probably going to become much more straightforward for you, but it's good to be able to do both because in many instances we can't actually do specific values because we aren't given a specific value. So what does this look like? Well, if you have f of g of x, it just means everywhere you have an x in your original function, so we have x squared, we are now subbing in for this x the entire g of x function. So what is the g of x function? The g of x function is 2x minus 1. That is what we just subbed in for the x in my f function. But I need to make sure that whatever my f function was, I am doing the same thing, and this is still all squared. Right? This was just x squared, and now I'm subbing in my entire g of x function into there. So I end up with 2x minus 1 squared. And in the abstract, we'd be stuck there because we can't do anything more. But if you need to solve for specific value, and I'll show you how this works over here after, right after, is, well, solve g of 3 first. So take your g of x function, but solve for g of 3. So sub 3 in for x, you get 6 minus 1. So g of 3 is 5. So that means that this whole thing is just worth 5. So then you're only solving f of 5 in your f function, which is x squared. So you get x 5 squared. So f of 5 is 25. So that would be your g of f of x when x is 3. Now, if we did it in the abstract like this, and then we plugged in 3, we get the same thing. 2 times 3 minus 1 all squared. Well, that's just 5 squared, which is 25. You would expect them both to work unless you've screwed something up, but we haven't, so we're good to go. So let's do a couple more, but you'll see in this case, you have to do the abstract because we aren't given a specific value. So f of g of x means we take our f function, 1 minus x squared, and we sub that out for, in this case, 2x plus 3. So what do I do with that? Well, I go 1 minus 2x plus 3, but all squared. And then we got to do our due diligence. We got to do our FOIL. So we're going to, this is just 1 minus, and careful, keep the brackets because you are subtracting 2x plus 3 times 2x plus 3, which means 1 minus, brackets, 4x squared plus 6x plus 6x plus 9, 1 minus 4x squared plus 12x plus 9. And that's why we keep the brackets, so we remember to water bomb that in. 1 minus 4x squared minus 12x minus 9. Group my like terms, and I'm left with negative 4x squared minus 12x minus 8. So you have simplified f of g of x. So you get, basically you get this new combined function, and you could call it something else now. You could call it h of x if you wanted. And you'll see on the right here we have similar scenario, except it's now g of f of x, and it's important, they're not the same. Okay, they're not the same thing. So g of f of x means we take our g function and now we're plugging in my f function. So I have 2, and then instead of the x here, I'm plugging in 1 minus x squared, and then plus 3. And now I just simply water bomb this one. This one's a lot easier algebraically. I end up with negative 2x squared plus 5. So you can see two very different answers depending on which function is being composed of which. So let's keep going. Here's an example we'll do in the abstract, and then we'll do piecewise. So we have two functions. So f of g of x means I need f of g of x, which means my f function x squared. I'm subbing in my g of x value. So again, now I have 2x minus 1 all squared instead of x, which means I have 2x minus 1 times 2x minus 1, FOIL, 4x squared minus 2x plus 1, so 4x squared minus 4x plus 1. So that's my abstract. But now I want, in the end here, I want of negative 2. So from this moment, I'll now plug in negative 2 for all my x's. Watch your brackets, watch your exponents. Don't want to screw up your positive negatives, because that's going to be positive 4 times, positive 4 times 4, which is 16, and then plus 8, and then plus 1, so 25. So again, here we've done it piecewise. In fact, similar to what we did all the way back here. Kind of got ahead of myself, so I'm doing it again, but hey, second time, third time, fourth time's the charm. And then remember, this one piecewise was first we solved for g of negative 2. Now in this case, we end up with 2 times negative 2 minus 1, which was negative 5. And then we plug that into the f function. So f of negative 5 was negative 5 in brackets, all squared means 25. So same solution, you would expect it. So what about a lovely domain and graphing these types of things? Well, it's really important that you consider the domain of both functions, and particularly the function you start with, because if you are composing f of the g function, you need to consider your g domain. And if we look at the domain of our g function, it's a square root, which means x has to be greater than or equal to 0. We're not allowed to have negative values under a root. So that is a big chunk of our necessary domain. It's very possible that the domain of our x function, which in this case is a parabola, this is all real numbers. So my f function has no stipulation in itself, but since it's being composed of my g function, my f of g function is going to need to contain the stipulation that x has to be greater than or equal to 0. It needs to contain both. The f function actually matters less than the g function. We need to satisfy the g function first because it is what we're being composed of. So let's do this. F of g of x gives us, instead of an x, I'm now going to plug in square root and then squared minus 1. Well, square root squared is just x minus 1. So we get this lovely new function, which is just a straight line. It has a y-intercept of negative 1 and a slope of 1. So we get a line that's going to look like this. But it does not go into my negative realm because I need to satisfy that domain. I cannot just satisfy my f domain. So you really got to pay attention to your domain, particularly your input function. So things are obviously going to get a little bit more complicated. So here is a complicated one. We need f of g of x, and we'll find its domain. So let's start by saying, okay, well, what's the domain of g of x? Right? Domain of g of x. Well, I can't have this, right? I can't have that be 0. So my domain, to start off right away, x is not allowed and will never be allowed to be negative 1. So let's just kind of toss that in the corner and let's remember that later. what we need to look at now. Now you might be thinking, well, what about f of x? You don't have to worry about f of x because we're not done with f of x, right? In this case, we're going to be combining these functions. So my f function technically won't exist when I'm finished. But since my g function is being used in my f function, I need to satisfy my domain of my g function first. So let's now do f of g of x. So that means everywhere I have an x. So here and here, I am now subbing in this whole function. So this is why I said things might get a little messy. So what do we have? We have 1 over x plus 1. That's been subbed in for that x. And then 1 over x plus 1, all plus 1. And it's going to be handy. All minus 1. Missed that there. It's going to be handy to get ourselves a common denominator on the bottom there. You want to combine these things on the bottom. So what's missing here is, well, we're going to need an x plus 1, and we're going to need an x plus 1. And be careful because we are subtracting. Because now we're going to have 1 over x plus 1 over 1 minus x plus 1 all over x plus 1. Let's simplify a little bit further. 1 over x plus 1 over 1 minus x minus 1, because this negative has to be water bombed, which is why I make big emphasis on brackets, and then all over x plus 1. Simplify again. 1 over x plus 1 over 1 minus 1 is 0, so negative x over x plus 1. Now remember, here we are dividing two fractions. So flip, multiply. So you end up with 1 over x plus 1 times x plus 1 over negative x. And now that will cancel with that, because you could put brackets around it, make it look like it's a thing, but they cancel out. And we just end up with 1 over negative x, which gives us negative 1 over x. And what is the domain of this? Because this is my new f of g of x. X is not allowed to be 0. So those are my two domain stipulations, that and that. I don't have to worry about my initial f stipulation because my f function is only being used in combination with my g function. So you can see that things algebraically get a little bit complicated. Let's look at a similar question, well, the same question, except this time we're going to do g of f of x. Now in this case, we need to take the domain of my f function. So x is not allowed to be 1, and we'll kind of keep that off to the side. Now this one is going to be a little bit easier because we're only subbing in for 1x. So we have this as my inputted function. And again, let's, I subbed in f of x, so that should be x minus 1. Let's get a common denominator. So what's missing from here? Well, x minus 1 over x minus 1. Now in this case, you're adding, so you don't have to be as meticulous with your brackets, but always helpful. So now we have 1 over x plus x minus 1 all over x minus 1. And we'll simplify through. So 1 over 2x minus 1 over x minus 1. And you can think flip, multiply, look at this however you want. You have 1 times x minus 1 over 2x minus 1, which just gives us x minus 1 over 2x minus 1. There's actually no simplification we can do there. That is our new one. And here we have a domain restriction where x is not allowed to be 1 over 2, 1/2. So we have a domain where we can't have x equal to 1 and we can't have x equal to 1/2. And this is my combined function, my composite function g of f of x. So you can see quite different from f of g of x, different domain, different final function, and a lot more complicated for the first one. So just because we are combining the two functions. If it's in a different order, we get a very different scenario. Now, what if you're just given a set of points? Well, if you're given just a set of coordinates, it's really the same thing. See, if we're looking for f of g of x, you have to do your input output for your g of x first. So if you look at your function g, you have three different inputs. So you're going to go, okay, well, what is, let me do this piecewise here, okay? What is f of g of a? What is f of g of b? And what is f of g of c? Those are the three different scenarios. Well, that gives me, okay, well, g of a kicks out a 1, so that gives me f of 1. G of b gives me 3. And g of c gives me a 5. Those are the outputs for those given g inputs. And then I plug that into my f. So now f of 1, well, I actually look at my f function here. And I go, okay, well, when I have 1 for my input, I get d. And when f is 3, I get e. And when f is 5, I get nothing. There is no 5. So, undefined. There is no function at that point. So what do I get for my composite function? My f of g of x is given by only the coordinates I can create. So a from my g, and then the output from my f of g, so a comma d, and b from my g function, and the output of the whole thing, b comma e. And again, that is all I have, that's all I can do. So let's keep going. Remember that this is about input and output mapping. So if we look at a graph, we look at our input and then we got our output. So if you want to know what f of g of 1 is, well, that's just it. Start with g of 1. So on my g graph, where's x equals 1 is here. So my output for g is down here at -3. So that means this becomes f of -3. And then, well, where's -3 for my x? It's here. And on my f function, it's 1. So f of -3 is 1. So that's how you get your solution graphically. If you have g of g of 5, which might seem a little redundant, you still need to find g of 5 first, because where's 5 on my x-axis? It's here. So g of 5 is actually 1. So then this becomes now not g of 5 anymore, but g of 1, which is a whole different solution, because what's g of 1? Well, g of 1 was down here, so again, it's -3. So you're just tracking on your graph input value to output value, and we're concerned with the output value. Now, this is one of my favorite things. I call this whispers of calculus because this is how you will eventually learn to calculate a limit or a derivative before you even know what a derivative is. But it all comes down to function notation, substituting, making composite functions. So in this scenario, we want this, okay? Now, what do we have? We have f of x, okay? F of x is given to us right here. What we don't have is this f of x plus h. Well, that just means in our f of x function, we now sub in x plus h. So we have 2, and then instead of x squared, it becomes x plus h squared, and then plus 3. Simplify this out, and you have 2 times x plus h plus 3, which is 2, and then FOIL that bit. So x squared plus 2xh plus h squared. I combined a step there. I hope you know what I did. And then you water bomb the 2 in. And that is our f of x plus h. And now we just throw it into our equation. F of x plus h, so 2x squared plus 4xh plus 2h squared plus 3. So that's f of x plus h, and I'm going to erase it because I just wrote it down. But now minus f of x, and brackets please, because we are subtracting, all over h. and now we subtract, subtract. So we get 2x squared plus 4xh plus 2h squared plus 3, but now minus 2x squared minus 3 all over h. And now that cancels with that cancels with that. We are left with 4xh plus 2h squared over h. And now since we have h as a common factor, we can cancel h. We can cancel one of those. We can cancel the bottom. We're left with 4x plus 2h. And you will see in calculus what happens to that after the fact. And then it's a lovely connection. And we talk about what happens when h gets closer and closer and closer to 0. So then you end up with just 4x, which is the derivative of that equation, but you will learn that eventually. So last thing I want to look at is decomposing a function. So what we've been doing is we've been composing two functions together, but how can we decompose them into two? And it's actually really straightforward. Look at something that looks like it's been implanted into another one. You're kind of looking for like a mother function and then something we've plugged in. So if we look at this, like this square root symbol really sticks out to me, right? And then this x minus 2 is something we could have plugged into it. So what if g of x was x minus 2 and f of x was square root of x, right? We plugged this in to that. So that's the connection you're making. I can't make it any simpler than that. You'll get good at noticing those things. If you see something like if you have a squared or a cubed or a root or an absolute value, like those are things that could be your outer function, and then whatever's inside that becomes your inner function. So here's another one, right? Here's a cube root. So, well, obviously f of x is just going to be cube root of x. And then what did I sub in for that x? Well, that's my g of x. G of x is x plus 5. And that would give me, right, that scenario would give me that scenario. Okay, so here's one where there's a lot more going on, but again, this cubed is kind of your alarm bell, right? And then this -2, well, it's just going to have to exist in your original function. So that means f of x could have been x cubed minus 2. And then all I did was I plugged in for that x my root x plus 1. That's my g of x, and it works. It fits. So you'll start to see these clearer and clearer. They come out with practice. Everything comes out with practice, right? So that is composite functions. Next, we're going to dive into our first look at transformations, and I've broken it up into 2 videos. And then we're going to work through section 2. This is a heavy section. It's got a steep learning curve depending on how long ago you looked at Pre-Cal 11. So just come in ready to learn, ready to try, ready to ask questions, and we will get there. Okay, take care.